magnetic field being experienced by this proton is affected by the protons on the neighboring carbon atom. So we use this rule called the n+1 rule. So the n+1 rule tells us the number of lines a peak will be divided into, where n is the number of protons on the neighboring carbon atom. So this peak corresponds to these hydrogen atoms. If we look at the neighboring carbon atom, it has 2 protons. So here n is equal to 2. N is equal to 2 and n+1 is hence equal to 3. So this peak is divided into 3 lines because the neighboring carbon atom consists of 2 protons. So n is equal to 2 and n+1 is equal to 3. Now, when we look at this peak, it is divided into 4 lines because when we look at this carbon atom, it has 2 protons and the neighboring carbon atom has 3 protons attached to it. So in this case, n is equal to 3. So n plus 1 is equal to 4. So that's why this peak is divided into 4 lines, because the neighboring carbon atom has 3 hydrogens attached to it, and n is equal to 3, n+1 is equal to 4. So you will read about this n+1 rule in detail in the next slide, but now before that I want to clear something out. So you might ask that this oxygen atom has a hydrogen as well, and as you can see, this peak is a single line, but the neighboring carbon atom has 2 protons attached to it, so it should be divided into 3 lines as well. So the thing is that whenever we have a highly electronegative atom like oxygen or nitrogen which is attached to a proton, so for oxygen it can be OH, so for oxygen it can be OH, and for nitrogen it can be NH or NH2. So whenever we have a highly electronegative atom like oxygen or nitrogen attached to a hydrogen atom, we don't get a splitting pattern for them. Like this peak is split into 3 lines. We will not get a splitting pattern for these lines. The reason is not in your syllabus, but I can share it with you if you want. So what happens is that hydrogen bonds, as we know, are stronger than all other intermolecular forces, but they are not that strong. They are not strong in magnitude. They are strong in relative terms. So at room temperature, these bonds, hydrogen bonds, are pretty weak. The bond between the hydrogen bonds that attract this oxygen atom to other hydrogen atoms in other ethanol molecules. So let me just give you an example. So there is a lone pair on the oxygen atom. It will form a hydrogen bond with a hydrogen atom which is also attached to an oxygen atom in the other ethanol molecule. So this will be C H H C H H H. Okay, so there is a hydrogen bond between these, and this hydrogen bond is not that strong. It is strong in relative terms. It is stronger than the van der Waals forces between the 2 molecules, but it is not stronger in magnitude at room temperature. So what happens is that there is a rapid exchange of hydrogen between these 2 molecules, and therefore hydrogen cannot stay here for a very long time. It keeps moving, and to give a splitting pattern, it needs to stay. So when we actually cool the entire molecule to a temperature to like -40°C, then we can actually get a splitting pattern. But however, we are carrying out all of these all this analysis at room temperature, and hence we will not get a splitting pattern. So what you need to remember is that oxygen attached to protons and nitrogen attached to protons do not give splitting pattern in any way. They do not contribute to the splitting pattern of other carbon atoms or of other hydrogen, of other peaks, and they do not and no other peak can contribute to the splitting pattern of this proton.